So there's lots of different ways to think about an angle. And one of them is it's a measure of a turn or rotation. Now, we have an interesting way to measure angles. We often use degrees to measure angles, but there's other ways to measure angles. And the idea of a rotation is a pretty straightforward one and related to a circle. So if we were standing in the middle of a circle, looking out in some direction, we could then stay in that position, fixed there, but we could rotate. Right? And if we go back, staying in that fixed position, facing the same way, that would be one complete rotation. So that'd be turning in a complete circle. And getting back to where you started. So the idea of complete circle here is back facing the same way. And I could go one full rotation. I could also go half a rotation. So if I started facing this way, and then I spun so that I ended up facing that way, the opposite direction, I could just say that the angle is 1/2 of a rotation there. When I look at where a wall meets a floor, oops, not a very good floor there, a little better, then the angle formed by the wall and the floor here could just be called 1/4 of a rotation. Right? We didn't go all the way around. We just went 1/4 of the way around. Complete circular rotation. So that's one simple way to talk about it. 1/4 of a turn, 1/4 of a rotation. Now we use this idea of degrees instead. So we also call this 90 degrees. Right? And a full rotation would be 360 degrees. And a half a rotation would be 180 degrees. Right? 360 as a whole, half of it would be 180. Half of 180, which is 1/4, would be that 90 degrees. But the question here is, why 360 degrees? And you happen to know why? Why would there be 360 degrees in a full rotation? You know, any idea?
I don't know.
Yeah, so it comes from a little bit of laziness and a little bit of reality. So where it comes from are days in a year.
Oh, I was gonna say that because I just did that in a lab last night.
Yeah, so there's 365 days in a year, but it's really 365 1/4 days in a year. Oops. And it's actually not quite a quarter either. That's why we have these leap years, but then every 100 years, there's another one. So days in a year is a little bit tricky. But even if we thought it was 365 days and every once in a while an extra day, the 5 was kind of awkward. 360 was just a nicer number. So there's 365 days in a year, but 360 is nicer.
And that's how long it takes for one rotation around the sun, right?
Yeah, yeah. So it's almost 360. 360 is nicer than 365, certainly nicer than 365 1/4. Lots of numbers divide into 360. It's got tons of divisors, which makes it, that's kind of its nice measure. It has many divisors. So it was decided a long time ago that just because of the way we rotate around the sun, and it's all kind of like 360 days, they chose 360. So in some sense, it's meaningless because it is sort of arbitrary. It isn't the number of days in the year. The number of days in the year isn't a whole number of days in a year, just because the Earth spins at one rate and we go around the sun at a different rate, and they just don't line up. And I doubt there's a planet in existence where its rotation matches on its axis, matches its rotation around whatever body it rotates around, like another planet or a sun. So 360 is a weird idea, but we're kind of stuck with it. It's there. Rotation and the idea of a turn is just a really nice way to think about it. And really, at first, kids only need a few ideas. Like, I can rotate once. I can rotate half a time. Right? Change direction, go the other way. 90-degree rotation is really nice because of the way we build things in terms of these ideas, what we call right angles. And then we have 360 to deal with. So we're stuck with it. Its historical significance is kind of hidden, but it's related to the days in the year. So there are a couple of other ways angles are measured. I'll talk about those another day, I think, but not today. But again, we have two types of measures right now. We have the idea of a degree. And that 360 degrees is one rotation. And we can just measure angles as a fraction of a rotation. That's okay too. A third popular idea is an idea of radians, and we'll talk about that next class. All right, other things about angles. Types of angles. So I mentioned a moment ago, if I can make a pair of line segments or rays or even lines meet like a floor and a wall, if this angle here happens to be 1/4 of a rotation, or 90 degrees, then we also call it a right angle. Sometimes it's referred to as a square angle. So right angle just means 90 degrees. But there are angles that are greater than 90 and less than 90. So if I had another angle, again, usually when we talk about angles, we have some kind of vertex. I have line segments here, but they could be rays or lines. So this angle right here is less than 90. So we would say this is an acute angle. And if we have an angle, oops, line tool, that's more than 90, so like this one right here, and this would be an obtuse angle. Let's just go in Geogebra and play a little bit. Getting a little messy. And again, I was just playing right here, so I'm just going to go to the menu on the upper left and just clear it and start over. asks me if I want to save it because I'm signed in. I'm just going to not save it there. So just playing with angles some more. Again, often when we play with angles, we use rays, but you could use line segments. I'm going to switch back to the ray tool down here under lines. And I'm going to make myself one ray. I'm going to let A be the common vertex. And so B and C would be called leg points on the ray or on the angle. A is the vertex of the coinciding rays. Then I'm going to measure its angle. And again, when you measure the angle, you could click on just the two the rays to do that. If you use the points, then the middle point has to be the vertex. And by middle point, I mean the second one out of three that we click on. So it measures that there. And remember, we can move that if it's in an awkward position. And then I can also move C. So here we can see I have, it's less than a right angle, right? I'm lower than 90 degrees. And sometimes if I can get, it's sometimes hard to get exactly 90. We have to kind of engineer that to happen. I can't seem to make it happen here, but I'm almost at a 90-degree angle there. And as I come around, I can get to, can't quite get 180 degrees. I'm trying, but it doesn't want to do it. But I can keep going around the other way. Now notice it changed how it was working. So right here, I'm at 179, almost 180. As soon as I go through to the other side, it starts measuring the other direction. And that's actually a new feature of Geogebra. Didn't used to do this. Interesting. All right, there's probably a setting for that, but a couple ideas related to this. Suppose I have 3 points, A in the middle, and B and C on each side. Kind of like I was playing around with just a moment ago. If I want A to be the vertex here, and I measure the angle from the AB side over to the C side, if A, B, and C are collinear, they all live on one line, and A is the vertex, then this has to be a 180-degree angle. If you have an angle that's exactly 180 degrees, the 3 points are collinear through the vertex. That's called a straight angle. It makes a straight line. Although Geogebra wasn't letting me do it a minute ago, I could have an angle that's more than 180 degrees. So actually, I didn't do a very good job drawing that. Try that again. I want that right there. So let's say that's point A there. This is point B. So remember, if I wanted to designate this as a ray, I would put A, B next to each other with a line and an arrow only on one side. So that would mean the ray starting at A going through B. Put a point there for C, and if I wanted to label that more carefully, I would say starting at A, going through C, make a ray. So that would be the ray AC heading that way, ray AB heading that way. And I could measure this angle coming through that way right there. So I was attempting to go here 180 plus another 45 if I drew it right. So would that be 225 degrees? And over on the other side, I could measure the angle this direction too, if I wanted to. So that would be 45 past 90 the other way, which is what, 135 degrees. And these two angles together make a full rotation. And so if I add them up, it should add up to 360 degrees there. So sometimes when we're writing down the measure of an angle, I might write the measure M of angle BAC. So this would mean starting at B with vertex A, head over to C. And typically angles are measured counterclockwise first. So that would be that 225 degree angle. And then for this other one, I would measure it counterclockwise usually. So that would be to measure angle from C, vertex A, go to B. That one should be my 135 degree angle. And there's probably a way to tell Geogebra to let me have an angle over 180 degrees. We'll look for that setting in a minute. So summary, we got 90 degree angles. So that would be a quarter turn. Less than 90, we call it an acute angle. If it's greater than 90, it would be obtuse. So both the 225 and the 135 angles, those are both obtuse angles. Straight angle, that means through the vertex, we have a straight line, 180 degrees. A couple more types of angles. So with a 90 degree angle, if I were to add another ray here, that breaks this up, let's say that right there, I was trying to make an angle down here that was 30 degrees, and another angle over here that was 60 degrees. These two angles together add up to the 90 degrees. Sometimes when we're doing angles, we use Greek letters for them, so I might call this one alpha and this one beta. And anytime you have two angles that add up to 90, so angle alpha plus angle beta, then they're said to be complementary angles. So let's try to make some complementary angles in Geogebra. So I'm going to reset this, clear, don't save.